Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to continue a series that we started this past spring focusing on classroom strategies for calculus to get you and your students ready for your end-of-course exams. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make those tough to teach, tough to learn concepts accessible to all my students. Tonight I'm really excited to be joined by our two panelists, Fan Disher and Vicki Carter. Fan has taught all mathematics courses from 7th grade through college algebra in her 43 years of teaching, and most recently teaching pre-calculus and AB and BC for the past 28 years. She's also an AP Calculus reader, wrote a Louisiana State curriculum for Algebra 2, and presents numerous workshops for middle through high school teachers about mathematics and graphing technology. She shares many of her calculus and pre-calculus classroom activities at state and national conferences, as well as in her store, Fan's Math, on Paid Teacher website. Fan, thanks so much for joining us.
I'm glad to be here, Mike.
And Vicki has been teaching high school math for 42 years and currently serves as the math department chair at West Florence High School. She's a former co-chair of the AP Calculus Development Committee and served as an exam leader at the AP Calculus reading this past summer in 2018. She received the T-Cube Leadership Award in 2015, and Vicki has served on TI-Nspire authoring teams and has presented at many national, state, and local conferences. Vicki, thanks for joining us tonight.
We're so glad to have everybody with us tonight.
We're expecting a large crowd, so your audio is muted. Feel free to send any questions you might have for Vicki or Fan using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar, along with a link for the documents that are being used by Fan and Vicki tonight. We hope you don't have any audio issues, but in the event that you do, try selecting Communicate from the very, very top of the WebEx menu and choose Audio Broadcast. At this point, Fan is going to discuss our agenda.
Hi, we welcome you back. I hope you came to the first part of this exam review. In the first part, we looked at derivatives and limits. Tonight, we'd like to look at the second part involving integrals. And I know some of you haven't gotten to all of these sections yet, but hopefully it'll be a good review when you're ready to look at it again. We're first going to start off by looking at accumulation. Of course, that's the big idea in integral calculus. And then we'll look at the fundamental theorems of calculus. We'll review those. Then we'll review particle motion, and then we'll look at some calculator skills on both the TI-84 Plus and the TI-Nspire.
Thanks so much, Fan. And Vicki is going to discuss our expected outcomes.
So tonight we want to revisit some accumulation problems, and we're specifically going to look at Riemann sums and trapezoidal sums. We'll also look at the limit definition of an integral and visit a few. Fan has some really good slides on that issue, and there are possibly some questions that could show up on the AP exam on that limit definition. We'll do a quick review of area volume. Length of a curve in BC is also one of the applications that is usually kind of grouped together with area and volume. We'll look at the two parts of the fundamental theorem of calculus with a few sample questions and a little quick exploration of particle motion as it relates to integrals in AB and BC. But most textbooks don't cover a lot with particle motion. It is a fairly popular topic on the AP exam, so we hope we can give you a little insight and some things that you might need to make sure your students can do with particle motion.
Thanks so much, Vicki. Fan, I am giving you control. Feel free to share your screen.
All right, can you see it?
Not just yet.
We'll try again. There we go.
Thank you.
All right, so welcome and to this second half on integrals. My part tonight is on integrals of accumulation. Now, you got to remember I'm from Louisiana, so we're in the Mardi Gras mode down here. So you'll see a couple just interesting slides here. There are three parts of accumulation I'd like to cover. We'll look at the Riemann sums, definitely the rectangles, and some trapezoidal sums. Then we'll look at a limit definition of definite integral. In part one, we looked at the limit definition of derivative, and now we're going to the integral. And then we'll look at some area, volume, and length of curve. All of these problems that we have in these slides, you can get on the handout, so don't try to just jot them down so fast. See if you can at least take one or two things away from this presentation tonight that you can use. So I'm going to start off with Riemanns and trapezoidal sums. Now, you're teaching it or have taught it, so we know the difference in left, right, midpoint Riemann sums. We know that's rectangles. Now, on the AP test, they don't say rectangles. So when they say left Riemann, your student needs to know that that means a rectangle with the left side being the height and so forth. Then, of course, there's the trapezoidal sum that the students are going to accumulate trapezoids to approximate an area underneath a curve. So we're going to start off here with a tabular function. Now, most of these Riemann and trapezoidal sums that I've seen on recent AP tests on the free response questions have been tabular functions. So make sure that your students can use a tabular function. I start off when my students have a tabular function, I make them write that change in x right above it, just so that it's sitting there, and they're not going to use a change in y, but they're going to use a change in x. And then I make them actually draw some dots and put the sides. And I don't care if they're exactly right or anything. I just like them to have that visual that they're going to have a rectangle at these dots with those sides. So this L of 3 would be a left Riemann. So the left-hand side is the height, base times height. So there's your delta x times your f of x. Your right Riemann would be the right-hand side that's on the curve as your height. Now, a midpoint Riemann comes up, but there's just not enough information in this particular tabular function that they can actually find the height from a midpoint. And then trapezoidal is this particular one, base 1 plus base 2 times height. They get confused when I say height here for trapezoid. I tell them to turn their head sideways. When they turn their head sideways, they see a trapezoid, and the height is the delta x, where the two bases of the trapezoid are F1 and F2. So I'll give you an example of here's a midpoint Riemann that they actually can work. There's your change in t at the top. Now these are even increments. This was not a calculator problem. It's number 3. Might have been a calculator problem in 2013. So and the increments were the same, but they had to get their height from the middle of the increment. That would have been your midpoint, 3 subintervals. Now, this particular problem asks them to find that midpoint sum with 3 subintervals, and then use correct units and explain the meaning of that particular integral. So there's your midpoint, so that you've got the 2 being the base, times the height, 5.3, 2 times 11.2, the middle, and so forth. Now, to get the correct correct units, they have to realize that 1 over 6, we're looking at an average here, an average amount of coffee. So that 1 over b minus a, which is your average formula, the b minus a is actually in minutes. So that the c is in ounces and the dt is minutes. I tell them play the units game, and it's going to work out so that your answer gives you the correct units. So this is the average amount of coffee. So there's your midpoint Riemann from a tabular function. In this particular example, this is not a tabular function. It's actually a function given to you in a multiple choice question. It was a calculator problem, but they actually asked for a left Riemann sum. Again, it's a calculator problem, but don't spend a lot of time trying to graph it. Just put a couple points there so that you can actually get a visual and see what the rectangles look like, and that's the left-hand side. Now, here's the confusing part about this one. When they put it in their calculator as a cube root, and we'll do this problem at the end. I'll show you how to put it in your calculator. Then you don't want to type it over and over again 3 times. They're going to do something careless when they're in a hurry. So I want to look at, when we come back to the calculator, how you can actually put it straight in your calculator and say the base is 2 times the height at 1, the left-hand side, plus the base is 3 to 6, times the height at 3, the left-hand side, plus the base, which was 2 from 6 to 8, times the height at 6, and come up with an answer. If they find each individual one and round it off, they're going to end up with a round-off error. They actually could have done the same problem in a list and found each individual one, but again, there might be a round-off error because your list doesn't show you that many places in your calculator. So those are simply 3 different types of accumulations for your left Riemann, your right Riemann. In your handout, you have a few more examples. I've given you a right Riemann, I've given you a trapezoidal sum, and I've also given you another left Riemann, I guess. Don't leave Riemanns and trapezoidal sums without reviewing. Now you have to review this before the end because they're going to forget it. Without reviewing, when is it a Riemann and a trapezoidal an over or underestimate? Because I've seen that particular question come up in some response questions. And the big picture is, if it's increasing or decreasing, that affects your left and right Riemanns. And I tell them just to draw 2 measly little rectangles and they can remember. So when it's increasing, a right Riemann is an overestimate. And your left Riemann's an underestimate. And when it's decreasing, the function is decreasing, the left Riemann is the overestimate, and the right Riemann is an underestimate. A visual worth 1,000 words. So remember to review that toward the end, right before the AP test. Now, midpoint Riemann and trapezoidal deal with not increasing, decreasing, but with concavity. And the midpoint is not that easy to see if it's an under or over like the rectangles were. The trapezoidal is real easy to see, so that if it is a concave up, the trapezoidal is an overestimate, and if it's concave down, the trapezoidal is an underestimate. So I just tell my students, just remember midpoint Riemanns are opposite of what trapezoidal is. So that if trapezoidal is over on concave up, then midpoint Riemann is underestimate on concave up. So there's your review on Riemanns and trapezoidal sums. Now we're going to do something a little special tonight because we want to have some kind of interactivity. You see, that's a float, by the way, and there's some beads. And I'm going to tell Mike, hey, throw me something, Mr. Mike, and he's going to throw a poll out to you just to see what kind of feedback we can get from you. The poll says, which accumulation problem do your students find the most difficult? And we're going to give you about 30 seconds to fill in this particular poll. So we're hoping you'll interact here, wake you up, and fill in the poll in about 30 seconds. And we're going to then show you the results.
And just a point of information, if you're on a mobile device, I don't believe the poll will show up. I believe it's only if you're on a desktop or a laptop.
All right. I hope you are clicking the poll. Don't forget, in the handout, there's some additional practice on a left Riemann and a right Riemann and a trapezoidal sum. So here's your results. Not bad. We had 93 people out there. 42 of you didn't get to answer. We're going to throw you something, mister, in a little while, but it does look like that most of you said, midpoint Riemann. Yep, I agree, because it's very important that they pick the middle of their section. All right, so what I'm going to do is, based on your feedback, I'll add another midpoint Riemann into the handout that we'll send you, or something. We'll figure out how we're going to get it to you. So here, let's go on. There's your results. the next thing we want to look at is the limit definition of the definite integral. Now, first part one, we looked at limit definition of a derivative. There always seems to be a problem like this in the multiple choice of the AP test, and my students have a lot of problem with it. Now, when you first started teaching this, you probably did something like this. All right, so I know I did. I was deriving how an integral comes from accumulating a bunch of rectangles, and this is what I did. I would always ask them to start off by partitioning the n subintervals and then finding an ordered pair, and it was a right-Riemann ordered pair. Seems to be the kind that keep popping up on the test. And then find the area of a simple little rectangle, and then find the sum. Now, I make them use those sum formulas just in the beginning, but then never again, because that never comes up on the AP test. And then take the limit. So what actually comes up on the AP test is they give you an integral like this, and they want you to pick the multiple choice that's in the limit. All right, so here's the definition again. I get them to draw. I always get them to draw a rectangle. So the first thing they have to do is find that delta x, b minus a over n, 7 minus 4 over n. And then I say, what's the point of your right Riemann? It's a sample point that starts at your a, the 4, and it's the delta x times I, or k. I've seen a bunch of letters in there. And then take that point and plug it into the function, which was the square root of x. Put a summation sign in front of it and put a limit in front of it. And that's what the picture looks like. So they do a really pretty good job of going from an integral to a limit, because it's not quite as difficult to go that way. Now, if you want to just kind of compare on the calculator to kind of convince them that that integral is really that limit. Now, you don't do this on the AP test, but it's just a really good exercise to convince them that the integral and the limit are the same thing. Then put the integral in your calculator. And we can't take limits in our calculator, limits of sums. Even in the CAS, we can take limits, but not limits of sums. So go ahead and sum it up from 1 to 1,000 and get an answer. And they're very, very close. That this is only 1,000, but they're very, very close. You want to know the beauty of this problem? Here's the question. Why is the summation an overestimate? All right, think about it. How did we know that rectangles were overestimates? And these are right Riemanns we're playing with. And you know it. If it's an increasing function, it's a right Riemann. It's an overestimate. And look at there, 7.014 compared to 7.013. It's just beautiful. So I'm going to go the other way, though. This is the direction my students have a problem with, going from a limit into an integral. Now, this one was in the 2016 curriculum frameworks, and it's the only answer it could be. So it was a really simple one, because this 1 over n, right here on the end of your summation, is your delta x, b minus a over n. And the only one of them, of the 4 that was 1 over n, was a. So I better not miss that particular one. But what about this guy? All right, this was an easy answer right here at the top, because the function was jumped to the cubed, and there was your 5 over n, so that would be 11 minus 6 x cubed. That was pretty good, but guess what? There are 2 more underneath here that are correct. 2 more, and I asked them to find which other 2 would be correct depending on how you are defining the function. So I'm going, all right, every one of them are 5 minus 0, 6 minus 1, 11 minus 6. Every one of those are 5 over n. So that didn't give us any way to eliminate them. So I said, all right, then let's find that sample point using the a that we started with, 0, 1, 6, plus the 5i over n. And then I tell them, plug that a into the function over here, the x cubed, or the 6 plus x cubed. and see if it actually makes out what the problem is, 6 plus 5i over n quantity cubed. And there's all your answers. And you see that these two, D and E, are both also correct. Now, they wouldn't have more than one correct on the AP test on multiple choice, but it might not be the obvious one, and that might throw them for a loop. In fact, they really might like A because, you know, it's x cubed. But that one's not correct. So I'll make them go through the steps. I hope that's helpful. There are all kinds of ways out there to explain it, but I've gone back and forth over the years trying to make heads nor tails of it for myself as well. All right, throw me something, Mr. Mike. We got another poll for them. Which limit definition of definite integral do your students find the most difficult? Can they change limits to integrals or integrals to limits? Think about it. I guess that's kind of hard to decide which one would be the most complicated for them. So we've got the poll up. It's only going to be there for about 30 seconds. And then Mike's going to give us some results. And then I'll put a few more problems on the handout based on your feedback. All right, Mike, what kind of results do we have here? Pretty even. Pretty even. Limits to integrals. All right, so I guess I'll find some more examples of both since it is pretty even. All right, I got one more accumulation type category for you. So this accumulation is where it's all going. It's going to find area, volume, length of a curve. But we're still accumulating, and I try to make sure my students know we're still playing with one little tiny function that we're adding up. So let's start with this particular problem. It's one of my favorites because I saw so many types of mistakes when I was grading it at AP. I think we were in Colorado in 2007. First off, when the students put this particular one in their calculator, they didn't do this. They did this. Yeah, that would be 20 plus x squared instead of 20 over 1 plus x squared. They would actually forget those parentheses. And this was, I think this was before, it was before the new operating system where they had a fraction bar on the TI-84. Now they have the fraction bar on the 84, and the Nspire encourage your students to use that operating system. The second problem they had with this particular problem was that they graphed it. It was a calculator problem, and there were so many students from this picture thought there was a vertical asymptote because they could not find the graph. Which, you know, if they were just thinking, if you put in an x of 0, you know it goes up to 20, so the world is not 10 by 10. So some of them zoomed out, and then it was so distorted, they did not know where to go from there. So we need to make sure we focus on finding that particular graph, setting the window some which way so that it's a graph that you can actually use. So here's what the function looks like. It's an even function. You needed to be able to find the points of intersection so that you could find the area. I always make my students draw a rectangle. Another problem we saw in Colorado when we were reading this particular free response question was that they wrote vertical lines instead of horizontal lines. But if they look at the rectangle and get the picture right, then they know to find the area. They are taking the top minus the bottom. Oh, and then they put the y1 as the top and y2 is the bottom. So this particular notation was perfectly acceptable to us readers if they told us which one was y1 and which one was y2, and go from a -3 to 3. So that was some of the problems that we found on this type of area problem. Check out this particular one. Now this was a 2006 problem, and they already gave them the graph. So they had to be able to find it. And there was 3 parts. They wanted area, and then they wanted volume. rotating around a horizontal line, and volume rotating around the y-axis. So let's talk area. They started with, they needed that rectangle, top minus bottom. All right, so it was much better if they would find those points of intersection and store them in their calculators in a letter so that they could use the letter A and B for the x's, and in part C, use the letters C and D for the y's. And then that way they didn't round off too early, and it saved them some steps. Here's what I saw. Now, whatever kind of problems you see there, well, there's several. First off, they rounded off their endpoints, and then they forgot the parentheses. They're just in such a hurry that when they forgot the parentheses, when they set up the problem, it messed up their whole problem. And I know they knew the math. That was what was so sad. So be careful with the parentheses. Learn to do this. And we'll look at this later when I go to the TI-84 to show you exactly how to do it. The second part was find the volume of a solid generated by rotating around that horizontal line, y equal -3. So now there's your rectangle, top minus bottom, identified y1 and y2. And so when you draw the rectangle, then you know you're playing with a delta x because that's the small piece of the rectangle. When you rotate it, it comes down like this so that you have an outer radius from the line y equal -3 and an inner radius. So when you end up with that particular function, y1 plus 3 was your outer radius, and y2 plus 3 was your inner radius, minus a -3, all right? I mean, x minus 2 plus 3, which was plus, that should be y2 plus 3. And then when you put it in your calculator, because you've stored your endpoints from your intersection, you can use them in your calculator, and you'll put your pi for integral from A to B with your formula for a washer. Now, part C, I don't have a slide for here, but there is a slide in your handout. So look that one up if you're interested in part C. Cross-sections. I teach cross-sections first, so they just don't throw pies all over the place. But cross-sections, I don't know why they have such a hard time with them. This one was a calculator problem. Notice number 92. That means it was a calculator multiple choice. But the two graphs were simple. They could have just graphed x squared and square root of y without a calculator. They needed to be perpendicular to the x-axis, so there's your rectangle. And they have squares sitting on top of those rectangles like that, and you are accumulating a bunch of squares. So the formula was the area of the face itself, which was side squared, but they had to figure out what was the side, and the side was top minus bottom, and then side squared, and the endpoint, then put it in their calculator. So that, and these endpoints were easy. I didn't need to store them as A and B. It would have been a really fast problem to be able to do. All right, so I put in one more on here, the length of a curve, and it's a BC problem. It's still accumulation. What are we accumulating? We're accumulating a bunch of little links. Now, when you derive the formula for this length of a curve, you go through quite a few steps, but you end up with this. So that you remember, if you would just put a sum of this, that wouldn't be a function times delta x. So when you're deriving it, you're factoring out the delta x and ending up with this particular formula. So that doesn't matter whether you're using an x's or y's. You could do dx dy or dy dx, but you have to go from x's if you're using the dx's. So my dy dx is 1 over x. This one really just asks them to set it up and not even go to your calculator and plug it in. Notice it was problem number 4, multiple choice. That's not even a calculator problem. All right, we're ready, Mr. Mike. Throw us something, Mr. This time the formula says, the question says, which volume formula do your students have more problems with? Do they have problems with disks, washers, or cross-sections? Now, while you're voting, I'll just tell you in your handout, you have a couple more problems. You have that part C, which is a volume by a washer around the y-axis, which is why you need to store the ordered pair y's in your calculator. And Vicki's going to demonstrate that on the TI-Nspire. And then there's a volume by disk. It was a multiple choice volume by disk. I haven't found FRQs using disk. They like to be able to score the student on going around lines other than the axes and using both functions. So you can use that. All right, there's your polling time. And what do we got? 32 cross sections. I agree. They get the disc. They definitely get the disc. But the 32 out of 97 of you wanted cross sections. Based on that feedback, I'll put another cross section problem in there. Now, when I come back after Vicki is finished, I'm going to show you how to store your X and a Y on the TI-84 from your points of intersection and use it in the formula. And I'm also going to show you how to put that particular problem that we had on Riemann's sum and use your Y1s and Y2s. I know this is not complicated calculator stuff. You might be interested in more detailed calculator stuff, but you don't need to know the calculator in detail for the AP test. You only need those core graph, find points of intersection, function, integral, and derivative there. All right, Vicki, I'm going to pass it to you.
Okay.
Stop sharing.
So I
and
found
I'm passing you the ball.
Okay. So I found it interesting that you also do cross sections first. I do too. I think it slows them up a little bit from doing the putting a pie in front of everything if they've actually done the cross sections.
Exactly. Exactly.
All right, so what I'm going to do is go through a few notes, and then we're going to head over to the TI-Nspire, and then we're going to come back and let Fan do some TI-84 stuff. So I'm going to talk about the two pieces of the fundamental theorem of calculus, different textbooks call different ones Part 1, Part 2, and then we'll look a little bit with particle motion and definite integrals. So the first thing is we have our two parts of our fundamental theorem. The top one I have typically called the evaluation theorem. Some textbooks actually name it that. But this is where the students actually learn how this process of a definite integral takes place and how to evaluate a definite integral. And the second piece, which I still am puzzled as to why students have difficulty with this, is how we take the derivative of an integrally defined function, which basically means your definite integral's lower limit is most likely a constant and the upper limit is a variable or another function. So in its most simple form, the derivative with respect to x of that definite integral would be f of x. So which part of the fundamental theorem, and I see Find got cut off by our beautiful Mardi Gras beads, but which fundamental theorem part of calculus do your students have the most difficulty with, the integral part, the integral of a derivative, or the derivative of an integral? So, Mike, if you can get that little poll started. And I think possibly the derivative of an integral, because it can appear in so many different forms. Sometimes we define the function as an integral, like maybe as an f of x, and then ask the students to find f prime of x. And then sometimes we use the notation, the d over dx, to indicate to take a derivative. I don't know if all the notations confuse the students, but for mine, it's probably that type of problem that's more difficult. So we'll see what our results are here. And it is the derivative of the integral. Took a pretty big lead there as far as the part that the students find more difficult. Okay, thank you, Mike. So let's talk for just a minute. I'm just doing some very brief slides here and then going to the calculator. So one of the things I try to give my students a visual about particle motion, and I am talking about the AB topic of motion on a line. Typically it's either motion along the x-axis or the y-axis, although it could be any line. I tried to get the students to realize that when we were in derivative world, that we took the derivative of the position to get velocity and the derivative of velocity to get acceleration. So I usually kind of draw this arrow that if you're working down this list, you're taking derivatives. So obviously, if we're working back up the list, if we started acceleration, we would get velocity when we took an antiderivative, and we would get position if we took the antiderivative of velocity. And sometimes this little visual helps the students a lot, sort of to get a mental picture of what they need to do. So we have another poll. So we got two quick polls here. In this case, which part of particle motion is, and we're talking about more from the direction of working with integrals, finding velocity from acceleration, finding total distance, and that means total distance traveled, and then also finding a new position when the students are given the velocity of a particle and maybe an initial position. So Mike is going to start that poll. Perhaps we should have added maybe total distance versus displacement, because those are two concepts that students tend to get confused. So we'll see what the poll looks like here, what the result looks like. And then we will look at a few problems. And the verdict is, okay, finding that new position. And I am going to address that a little bit because I think it's something that students get confused about with other things that they've actually learned. So that topic of displacement versus total distance traveled, displacement is just a definite integral from time 1 to time 2 of your velocity function, whereas total distance traveled is integrating the speed function, which of course I wrote as the absolute value of velocity. And this is the part that students forget, that they need that absolute value, or they need to at least think about the velocity being always positive, or like reflecting a graph. If the velocity function has a part of the graph that's below the t-axis, they might reflect it so that they can find the sums of the areas and get total distance traveled. And then I actually try to teach my students that there is, and I show them where it comes from, which is the fundamental theorem of calculus, but how we can actually compute a new position, knowing what I call an old position or an initial position and the displacement. I mean, it's a very simple idea. If they know where their particle was located, that would be an old position, and they add the displacement, they will have the new position. But if they kind of begin to see it that way and know what to do, I think it makes it a little bit easier, especially when they're using their calculator. Okay, so that's the end of our little slideshow. So I'm going to go to my TI-Nspire. We're going to do a few minutes with it, and then we'll go back to Fan so that she can do some TI-84 things with you. So I've got a couple of slides. First, some of the slides are just information, and some of the slides are actually doing a few problems. So this is a statement of the fundamental theorem of calculus, the evaluation theorem part that I had on the slide earlier. And then basically I just transformed that into a different expression, and this is, so I call it the re-expressed form of the fundamental theorem with my students. So we say that f of b is equal to f of a plus the definite integral from a to b of f of x dx. Of course, where big F prime is the derivative of big F is little f. This is the exact same thing I just had up about new position with velocity. So if the students start to see a correlation there, it'll be a little bit easier for them. So here is a problem that has been on a previous exam. We have a function h of x, which is 1 over the square root of x to the 5th plus 1. We are going to state that g is an antiderivative of h, and we know that g of 2 is 3, and we want to find the value of g of 4. One of the mistakes students make is they think they can take an antiderivative of h of x and So they find a g of x plus c, and then they want to substitute the 2 and the 3 to find c. Well, unfortunately, that's going to be sort of hard to do for the students. And these kinds of functions are created in this special way so that we are sort of telling the kids, you need to know how to use your calculator to do this. So if we wanted to find a value of g of 4, we'll use that re-expression of the fundamental theorem. So we would, and I've basically got a split screen here so that I can do my calculations below. So we have g of 2 is 3. So this is our initial value, or our what I call our old value. And we want to add the definite integral. So I'll go to my templates page, and I will get my definite integral here. And I want to go from the time that I knew the position, so that would be at 2, and my upper limit needs to be the time that I want my new position, that would be 4. And then I need to put in my h of x function, and I'm going to use my fraction template. So it's important, even on the TI-Nspire, that students use their fraction template to make sure they don't, except I just managed to get 2 of them there. That was sort of interesting. Okay, I want a square root of x. Let me get rid of that thing. Of x to the 5th power plus 1 with respect to x. And we would have our answer. It's hiding it here, actually. And so there it is, and this would be a calculator active question, most likely multiple choice, and so they would have to pick the correct answer from the choices. So let's look at another situation. In this case, we were given a graph of a function. This is also a fairly recent question that was in the curriculum framework. So they have a graph of f, and they have a defined g of x. And so g of x is the definite integral from 1 to x of f of t dt. And we want to find g prime of negative 3. Well, if we remember the other part of the fundamental theorem of calculus, then we would realize that if we took the derivative of g, it would simply be f of x. So the derivative of g is f of, or the derivative of g at negative 3 is f of negative 3. And then the interesting part here is the students have to realize what the slope of this segment is, or realize how, that we have a horizontal distance of 2 and a vertical distance of 2. And so that point, g prime of negative 3 would be f of negative 3, which would be positive 2. So this is sort of an interesting way to incorporate graphs. There's no calculator needed for that. I just have it up on the calculator screen. So then let's look at a problem such as this. So we have, in this case, f of x is the definite integral from 1 to x cubed of 1 over 1 plus the natural log of t. This is also a question that came from a fairly recent exam or from the curriculum framework. So it's no calculator. But one of the things I like to do is confirm what we would get working paper pencil with the calculator. I think sometimes the students, I don't know, maybe they believe it a little bit more if they see it happen on the calculator. So on this lower part of the screen, I've actually defined this function. If you see the f of x and then the colon equals, that is defining the function as this definite integral, and it simply says done when that happens. So now I want to find the derivative at a point. So I'm going to go to my little box here, going to go to menu, going to go to calculus, going to go to derivative at a point, and I want at x, and I want the point to be, I can't remember what I wanted, derivative at 2 or 3, I think. Let's put 2 in. Oh, it's 2. Very good. And since I have defined the function f of x, all I have to enter now is f of x and press enter. And then it's kind of neat to talk to the kids about what happened here. So we have, if we take the derivative of f of x, we would have 1 over 1 plus the natural log of x cubed, then times chain rule 3x squared. So 3x squared evaluated at x equals 2 would be the 12. But this gives you a good opportunity to talk about the laws of logarithms and how the log of 2 cubed became 3 log 2. And my students, seem to just be constantly baffled by that, and we have to review the laws of logarithms frequently. But I think that's just a neat way to confirm some things that they know how to do paper pencil-wise. Okay, we're going to look, I'm going to actually skip that one. I'm going to look at one more because I want to get to Fan's part. This is interesting because we pulled some questions to look at, and this type of question popped up frequently. Instead of giving them a position and a velocity and asking for a new position, we instead gave them an acceleration function and a velocity and asked them for a new velocity. Do you see the parallel to that re-expressed form of the fundamental theorem of calculus? So obviously, all I would need to do here is 5 plus the definite integral from, we have our initial time is 0, and we want our new time at 3. And again, I defined that function ahead of time to make this quicker. So I can just enter a of t, and then with respect to t, and I would have my new velocity. But I just think this is a really neat question to see if students understand what is actually going on with using both the fundamental theorem and the connection of acceleration and velocity. Okay, Fan, I am going to stop sharing, and I am going to send it back to you so that you can play on the TI-84 a little bit with everybody.
All righty. Now, can you see my screen?
We do. We see your calculator.
Hey. I can't pull it. No, we did it. All right, 2 things I told you I'd like to make sure that you know how to do. The first one dealt with this particular picture where we were finding points of intersection. I've already put the 2 graphs in there. Finding, there's your 2 graphs, and we want to find the point of intersection and store them so to use it in an integral. So, of course, intersection is second calc. Number 5 is intersect. And it asks for which curve, second curve. And you want to be closer to the point. And you can go closer to the intersection. There's an x and y. You're going to need the x's for part B, and you're going to need the y for part C. And you don't want your students writing them down and rounding off too early. So we're going back to the home screen, second quit, and we're going to take that X, and I tell them just press X and see. Oh yeah, there it is. So then we're going to say X, store it, and I'm going to put it in A, in alpha A. There it is. And then I'm going to pull up the Y, which is an alpha Y, which is down here on the 1. And I'm just going to press enter. Yep, it is. So I'll have alpha Y, store in, and I'm going to put it in C, alpha C. There we go. And I'll go back to my graph and get the next point of intersection. Second calc, intersect. Enter, enter, and that point of intersection is close to 1, 2, 3. So I'll just press the number 3 this time as my guess, and there it is. There's your 2 points of intersection. We'll go X store in. This time we'll put the X in B, and then we'll put Y, alpha Y store in D, and we can put 2 commands on the same line, but they forget how to do that. So I don't want to do that. So I have put the 2 functions in y1 and y2, and log of x is on top. So there's your top minus bottom. So now on the screen, I can pull up the integral, which is alpha window, which is F2. There's 4. I'm going to put in the A and the B. And this was the error problem, so the formula would have been y1 minus y2, and under alpha, the trace is your y1, and minus alpha on the trace button is your y2. And if you don't see these F buttons hot, that means you have upgraded your operating system. Please do that on the TI-84 Plus Silver Edition. I think it's 2.55. Then you press enter, and there's your answer without rounding off the two particular parts. All right, the second thing I wanted to show you was this particular problem, the cube root one, so that we could put it into the calculator with the y1. I'm going to clear these two out pretty quickly. And remember, cube root is under math, number 4, and that was 10x minus 84. You just don't want them to have to type this over and over with the new numbers in it and make something careless. Whoops, like I just, there she goes. Minus 84. 60. Now, I'm not going to graph it. I'm not going to look at it. I've just made it in Y1 so I don't have to type it every single time. And if you remember that in that particular problem, the bases were from 1 to 3 and 3 to 6 and 6 to 8. So all you have to do is put in a 2. And now up your y1, which is the alpha y1. And it's function notation, just like f of x, it's y1 up, and it was that was the left-hand side of your Riemann. And add it to the base was 3, alpha y1 again. Evaluate it at, you need the parentheses, just like function notation. And then plus the base again was 2, and the y1 evaluated at 6, parentheses 6, and you got it without rounding anything off, without having over and over again with zero errors. So all right, Mike, it looks like I can go back to you, and you can close us out on here. Vicki, you got any more you want to show?
No, I don't think so. I know we spent a little more time on theory than calculators, but there have been a lot of other webinars that you can go back and view, a lot of them on calculus that will give you a little more with the use of the calculator. So what we really hope is that you think about some of the problems that we have shown you and some of the things that we know are important for the AP exam, and we'll work with your students both with the calculator and with the concepts. And hopefully everybody's students will do really well in May.
Fingers crossed.
Good luck to everybody.
Thanks so much, Fan and Vicki. As we wrap things up tonight, there's a couple things I do want to share available on our website, education.ti.com. Let's try that one more time. There we go. First thing is, we did mention at the beginning that this is part 2 of a end-of-year exam prep series for calculus. And say you're looking for part 1. On our website, you can slide under the Professional Development tab and then go down to Webinars. And all of our previous webinars, including the part 1 webinar, have been archived and are available on demand. And so you can click on demand webinars, and you can either scroll down because it was pretty recent, or you can filter and select a topic. But classroom strategies for calculus end of course exam success part 1. And you can download documents and watch the video for part 1 as well. The other thing I wanted to share that I think I've been using personally in my calculus classroom that is still fairly new as far as availability on our website is under the Resources tab. There's a TI in Focus for AP Calculus. And so you can either pick a year or pick a topic. So say you pick Fundamental Theorem of Calculus. You can pick a specific year that you want to look at as far as the exam. And once you do that, just take a brief look here and just see some of the resources that are available. My personal favorite that I've been using with my students, if you slide down, there are PDF slides that were created, and they really do an excellent job of helping teach that concept with your students, give them some problems to think about. And this is all written for both the TI-Nspire as well as for the TI-84. So regardless of the technology that you're using, we have support for you. So please feel free to visit our website to learn more about that.
And Mike, let me just say one thing there. So even if the problem were not a calculator active question, we still give resources. So kind of like to help with how a calculator can give them some initial knowledge or maybe enhance their learning even though they wouldn't use it for that particular question on the exam.
Thanks so much, Vicki. So the T-Cubed International Conference is coming up quick. It's coming up early March in Baltimore this year. It's a great place to meet people like Fan and Vicki, attend sessions, learn more about your content area or about connecting different technology and pedagogy with content, and also just be around people that think similarly and appreciate the use of technology in the classroom like we do. So please feel free to visit our website to learn more. The other thing that we're doing to kind of get prepped for the international conferences, we're doing a slow chat book study. I'm going to put in the chat window the link for the book that we're reading. It's called Save Our Scientists, and it's each week on Twitter. People are reading portions of the book and then just sort of tweeting about it, about their thoughts and their reactions. So it's nice because if you haven't even started reading the book yet, then you can download the book. It's actually a pretty short read, and then start catching up on Twitter, so you wouldn't necessarily be behind. When you leave the webinar tonight, a brief survey will automatically appear in your browser. Your feedback guides us as we plan future online events, so we really hope to share your thoughts in that post-webinar survey. To receive a certificate of attendance, go ahead and click the link in the chat window. Also listed is a link for the documents. One thing I want to mention here is Fan and Vicki did a lot of work putting these documents together. And as you might have heard, Fan mentioned tonight she's going to do a little extra work based on the results from tonight's live polls that we took. She's going to be adding additional documents. So feel free to download the documents from the webinar for tonight. In a couple of days, you'll automatically get a follow-up email. So in case these links aren't working for any reason, or if you want to wait, that's okay too. But check your email in a couple of days. You'll automatically get that follow-up email, and in it will be a link to the recording, so you can play this back and kind of go at your own pace, a link to the certificate, and a link to the documents, which would then be updated. So the current documents link is as is, and then Fan will be doing some work to update it, and we'll get that done in the next couple of days. And if you're watching this on demand, go ahead and copy that link into your favorite browser.
We'd like to.
Go ahead. Sorry, Fan?
Well, we'd just like to thank everybody for playing along with us with the poll. We just thought it would be an interesting change in some of the webinars.
I agree. Thanks so much. So on that note, thanks so much, Vicki and Fan, for everything you shared tonight, helping us get our students ready for the upcoming end-of-course exam in calculus. Thanks so much.
Thank you.
Thanks a lot.
And
good night.
For joining us tonight.
Thanks for joining us.
I second that. Thanks, everyone. Hope to see you back online real soon. Have a great night.